if the lid is facing away from you. I want you to take this sample out, close your egg carton, and put the sample off to the side so everybody can observe it. You've already seen this sample tape. So we're going to use this to model how to do our mineral tests. The first test that you do with a mineral is the color test. We've already said this is the least reliable, but you still have to make this observation. So on your table, 1.3, sample number 1, I want you to record the color of this mineral. We're not talking about that you can see through it or it's shiny, it's color. What color is this crystal? And colorless is absolutely an option. So why do you think color is not reliable?
It's very subjective.
So you can make
It might be,
keep
yeah.
the zirconia clear too.
True. So this mineral has a definite chemical composition. What if there's impurities in here? Is that going to change the way it looks? Is that going to change the color?
Yes.
Absolutely. So pure samples are not all the way, they don't always occur. There's going to be elements that are going to be mixed in there. Sometimes it's impurities, and those are going to reflect different colors. So this one is colorless or transparent.
I need white.
You need a pencil.
I do.
So the color that you got is no color or colorless. Okay, everybody with me on the color? Yes, ma'am. It doesn't work. No, it does. Okay, the second characteristic we're going to look at is luster. Luster is the way that light reflects from the surface of the mineral. So how does light reflect from this? Does it shine like a metal? If it does shine like a metal, then all you need to do is record metallic. It has a metallic luster. Does this look metallic? No. It does shine, but not like a metal. If it is not metallic, then you say not metallic. Now, if it is not metallic, there's several ways that we can describe a non-metallic luster. It can be glassy or vitreous. It can be pearly, silky, waxy, or earthy. Now, don't worry about writing all of these things down, because we're going to have these listed out for you at a station where we're going to record the luster. However, on your graphic organizer at the bottom, the physical properties are listed on this graphic organizer, and the non-metallic descriptions are at the bottom. There's 5 of them listed for you. From left to right, glassy or vitreous, pearly, dull or earthy, waxy or silky. So the luster of this sample is non-metallic. It's glassy. It looks like glass. Dr. West? Is Dr. Brown around?
She's right back.
Okay. Okay, the next property we're going to look at crystal shape. I don't have these samples in front of me. You're going to be referring to some crystal structure samples that you're going to receive these for your classroom. Here's an illustration of these structures. So you're going to compare the crystal structure to the models that we have at our crystal shape station. So you need to look at it. Is it an individual crystal? Are there any crystals at all? Pam,
Is that anywhere on our graphic?
the crystal structure?
104.
Did I miss it? Or is-
No, it's not on that document.
This appetite?
Yes, it is. Thank you, Pam. Yes, after your table 1-3 chart where you're recording your mineral characteristics, this table is listed. So you can compare your crystal structure to the table or the three-dimensional models that we will have for you. Quentin?
I may be getting ahead, but I was just gonna ask, so when you're not looking at the whole form of the crystal, because like it comes to a point, you would take a cross section,
No, you are looking at the way it forms.
the way it forms?
Yes.
Okay.
Yes, you're looking, because if you took a cross-section, it would just be a flat edge. And you can't observe the atomic arrangement with your eyeballs.
Yes,
You're observing the way the crystal forms,
okay.
because that reflects the atomic arrangement. So this one, for example, if you look at it from one end, you see 6 different sides. And then if you look at it at the top, you see that it makes a prismatic shape at the top with 3 different sides. So what does it reflect here? Can you see which one of these models reflects this 6-sided crystal? So this 6-sided matches up with hexagonal. It's 6-sided, it is hexagonal. This was one of the differences in this clear crystal that you received in your first, that tackle box that you looked at with rocks and minerals. There was another clear crystal that looked just the same, but its crystal structure was nowhere near this one. That was one of the distinguishing differences that you could immediately say, oh, those are 2 different minerals, because their crystal structure is dissimilar.
So if you take a rock, can I ask a question?
Yes, ask a question.
If you take a rock, and maybe you have a large one, and then you take a hammer and you hit it, will it naturally fragment according to its crystalline structure?
A rock or mineral?
Mineral, so if you take a large piece of mineral, and you hit it, will the pieces fragment in their natural structure?
Sometimes they do.
Sometimes they do.
Yes. And we're going to get to that in just a minute.
Oh,
Okay?
Doesn't it have to do with like a diamond, what's a good cut and a bad cut or something
Nope.
like that?
Well, I think that has to do with it.
The way it breaks off or, no, oh, just one.
Okay, the next one, so we've got that this crystal shape is hexagonal. Do you want to address the crystal shapes?
Sure. That's what I did, right? Okay, so just to make sure about the shapes, if you'll look, we're looking at this. The names of the shapes. So A there, it's a cubic crystal. The name almost tells you the shape. What does cube mean? Tanya?
Kathy just told me the answer, it's six-sided.
It is six-sided, but it's more special than that.
Has 6 faces.
That are,
We're trying to help her.
don't,
You don't need anybody's help.
thank you.
She has a college education, y'all.
I have a therapist also.
I'm sorry, you said congruent. So all 6 sides, all 6 faces must be congruent, which is, let's get back on task, which is different from B. Okay, it's called an orthorhombic crystal. I have no idea what orthorhombic means. Rhombic. And now I know what it means. Okay, so in mathematics, we would call that a what?
Oh, rhombus.
Rectangular prism, but a rhombus has all sides congruent.
Right, this one doesn't.
This one does not. So there's a little difference there in math and science.
Rhombi do not have 90-degree angle, and this one has, it may,
Unless it's a square.
but if it's not a square, it doesn't have 90-degree angle.
Yes. So I'm wondering if the name of that has to do with the axes rather than the size, the shapes. Okay, so the axes, if you were to connect them, perhaps, the edges, the tips, the ends, would form a rhombus? Rhombus?
Sure.
Okay, we'll go with that. Okay, and then a C, a tetragonal crystal. Tetra in mathematics usually means what? Usually means 4. So, I need to tetra. Tetragonal.
It has 4 axes. 2 equal axes and 1 unequal.
So 2 equal axes and 1 unequal axis, and the vertical one appears to be the unequal. Okay. And the hexagonal? 6 sides. I tell you what, I'm gonna let you handle the rest of this, because I am just not sure about them.
They're all rectangular.
They are, except for the hexagonal, they all look like rectangular prisms to me. So it must have a whole lot to do with the axis, and not being science, I'm not sure.
Okay, all right. So what these, just read these. It's all about the way, the number of axes and the angle of the rotation of the axes. The length of the axes don't always matter because crystals don't grow according to diagrams. They may grow longer, they may grow shorter. The size of the crystal is determined by the amount of time that it has to form. So if it forms quickly, you're going to get little microscopic crystals. If it has a long time to form, then those minerals continue to grow and grow slowly and the crystals are bigger. So you just need to keep in mind the axes and the angle of the axes. Okay, the next characteristic we're going to look at is the streak of a mineral. Okay, the color of the mineral does not tell you exactly what the streak is going to be. And the streak is just, what does the powdered mineral look like? So the streak is the powdered form of the mineral, and we do it on a white, porous tile like this so that you can get an accurate observation of the color of the powder. So take your clear crystal and scrape it across your streak plate. Gently, you only have to do it once.
Oh, sorry.
If you want me to run my fingers on this chalkboard, I can do that too. Okay, now, if the mineral is harder than the streak plate, nothing's going to come off of that mineral. So you will get no streak. Like this crystal, left behind nothing. You might have scratched off some of the streak plate. I don't know. So you just record no streak on this one, or none. Now we're going to get to the fracture and cleavage part of this. The way minerals break is called its cleavage. What? Yes. So minerals that have cleavage, when you break them, they're gonna break into faces. You're gonna see like specific faces on the broken pieces. So if you crack open a mineral with a hammer, you break it open, it's going to break and you're gonna see crystal faces on it. Those crystal faces don't always look exactly like a crystal growth, right? Is that what you were saying?
I guess I was wondering how did, I guess the smaller question would be, how did they get their, if you said these are in their natural formation, how did they get to that formation? Is it broken?
They grew like that.
They grew
And
like
some of these pieces were broken.
off of things that grew for a
Yes.
longer period of time? Okay.
Yes. So this top sample, you can see that it broke and it still has some flat edges. Some minerals, when they break, even though they may have a beautiful crystal structure, when they break into it has no crystals on it. These fracture.
Okay.
Yes. There's no crystal structure, it's just
So
curly
you just say
breakages.
fracture or
They
crystal?
fracture. It either
Oh,
cleaves
sleeves.
or
Okay,
it
so
fractures.
sleeves.
Now, if we were getting into deep analysis on this cleavage, there's different types of cleavages. And so you would look at how it cleaved and describe that, but that's a whole other 3-year period. There's a cute little ballerina in the hall.
Is it Melissa?
She's way cuter.
So we are not going to break open this sample. We're gonna have several stations in another room for you that are already broken. So we have petri dishes like this, and you're gonna observe with your smart scope the cleavage or fracture of these samples. I'm sorry, I have taken that. No, that was not. Okay, that was not. This last one. And here it is. Not with your smart scope. We have these little microscopes for you to observe. If you want to carry your smart scope with you, you are welcome to, but we're not going to have one set up at this station. So this one, fast forward. Look, we looked at it. It's fractured. There's no cleavage. It's fractured. So when this one breaks, and you know, on mine, if I put on my glasses, the end of my crystal, I can observe where it has fractured from another piece of the crystal. So you can see an area where you have that fracture.
So, right, like it was like a huge, so they broke it off. So this is where you would check.
Because I think a fracture
Combining concrete.
Okay. Next, we've got our hardness test, and this is where you're going to need to use your kit. This station, this property of the minerals you can do at your table. Not right now for all of them, but this is something, we're not going to have a station set up because you don't need it. There's a scale for rating the hardness of a mineral. This is called Mohs Hardness Scale. And in your handout, I have a copy of Mohs Hardness Scale. Right after the crystal shapes page. It's a ranking of 1 to 10. If it scratches easily with your fingernail, then we rate it as a 1. If it scratches your fingernail, then it's a two. If it scratches
Your
with a
finger.
penny, if a penny can scratch the mineral, not if the mineral scratches the penny, okay? If a penny can scratch the mineral, that's a 3. If a nail can scratch it, but a glass cannot, I'm sorry, if it will not scratch glass, but a nail can scratch it, then it's a 4. If it's difficult to scratch with a nail and barely scratches the glass, it's 5. So there's this scale. Quartz scratches a steel file and glass. So we can scratch our fingernail on here, we're not gonna scratch it. Pull out your file, and run your file over it, and you're not gonna scratch it with the file. But you can scratch the steel file with it. Now the glass in here, there's a glass plate. You take your sample and just scratch it. You're gonna have to do it firmly. Scratch it on the glass. I see that my sample does scratch glass. And so I'm going to give this a 7 on the hardness scale.
The outside, say, any scratch.
Like it was gonna break it.
Scratch a steel file.
I didn't mean to. No, that's like a carpet.
No, did it break that?
Here's a Moe's.
That's what I'm saying, then what you first, is that breaking?
So the feldspar, this would be scraped with feldspar with the steel file.
It's not gonna break.
Okay, has anybody ever had glass cut?
How they cut by glass?
Listen, what do professionals cut glass with? Glass is pretty, no, not a saw and water,
Diamonds.
with diamonds. Because diamonds are harder than glass, okay? So diamonds are the hardest mineral. So down at the bottom, the hardest mineral is a diamond because it cuts everything. Okay, so the hardness is more than 6.5, and we're gonna, I would say 7. We don't have any other tests for these other harder ones. So we just know that it is more than 6.5 or 7. So you could write 6.5 plus, yes, or greater than 6.5. Okay,
That was 6 what?
6.5 plus, or 7 plus. The next test that you would use to identify properties of a mineral is called a specific gravity. Now this may get a little confusing, so I need your attention up here to really focus on what I'm going to show you. The specific gravity of a mineral is similar to the density, it's related to the density of the mineral. But density changes according to like your elevation, right? If there's less pressure on an object, then it's going to take up more volume, and so its density changes. The object doesn't change, but its density might change a little bit. So we have, so we compare it to the density of water. So the specific gravity of an object is the density of an object compared to the density of water. So it's a ratio, okay?
At a specific temperature or not?
No, at any temperature. So if we took the specific gravity, if we took the density of water here, it would be different than the density of water at the International Space Station. It's still water, but the density will be different because the volume might change
So in
according
the
to
same
the.
location?
Yes,
So,
in the same
in the same
location.
location.
Very good, thank you. So what we do as scientists then is we would find the density of water, and then we would compare the density of the mineral sample to that density of water to find the specific gravity, okay? We're gonna simplify that today. We're gonna assume that the density of water here in San Marcos, Texas State, in 243 is 1 gram per milliliter, okay? And that's gonna make things way easier because the specific gravity of our sample, so the true specific gravity is the density of our sample divided by the density of water, okay?
So you're not,
It's a ratio.
yeah.
Now, if our density of water is 1 gram per milliliter, then all we have to do is find the density of our sample. Now, because this is a ratio of densities, what are the units going to be for specific gravity?
Grams.
Y'all just think for a minute. Density in grams per milliliter divided by density in grams per milliliter equals,
1.
Doesn't that equal 1?
what are my units? Grams per milliliter divided by grams per milliliter is 1.
We don't have it.
So there are no units, it's just a number. Okay?
Tricky.
All right.
Oh, I see what you're saying.
So even though we are finding the density of the mineral at our stations, at our specific gravity stations, you're finding the density, but your specific gravity will have no units. Okay? So we are effectively saying that the density of the mineral today is equal to the specific gravity because our denominator is 1. Are y'all with me? All righty. So there's a table in here for your use on specific gravity. When you're doing your calculations in there, you can do them all on here and then transfer the specific gravity data to your mineral characteristic page, okay?
Can I give them a real world example?
Yes, go
They
to
have the little thing, little bulb thing that if you want to check the acid in a battery, you siphon up some of the, into the tube, the little spheres that they have inside will go up and it just gives you a number. That's it.
Okay, so you don't always have to have a unit.
Right.
Okay. Let's pretend we measured this and the specific gravity of this sample is 2.6.
That would be
So in your chart, table 1.3, record 2.6 as the specific gravity of sample 1.
Language.
tenths.
2 and
2.6.
6/10. Thank you.
Does the hardness say less than 2 5/10?
That changed, didn't it?
I thought it, yeah, I thought it was,
Yeah.
Yes, it's more than 6.5, yes.
Right.
Yep. Yes, I need the crown. Yes, ignore that, that was wrong. I don't know why it changed. Edit. Where is that? Okay, that's supposed to say,
greater
Okay,
than.
thank you. Thanks for catching that. Okay, we need to move on. Table 1.3, okay, the next one is the acid test. If you put a dropper full of hydrochloric acid on some minerals, they're going to react to the hydrochloric acid. This is a definite mineral characteristic for, that's a different reaction, definite reaction for certain minerals that's going to really help you out in the field. Some of them look like just the same, but if you put a little dropper of hydrochloric acid on it, then you say, oh, it's not this, it's this. So in your kit, you have a little bottle. We're not using it because we're not handing out acid. We have a station in the other room with hydrochloric acid. You're gonna wear goggles and be safe. A little dropper on our samples, not on yours, because if you continually drop acid on a mineral sample and it reacts, you're eventually not going to have a mineral sample anymore. So a positive test, evidence of a chemical reaction includes the production of a gas, which is what you will observe here, that a chemical reaction occurs producing a gas, which will be seen as bubbles. So this sample, when we put a dropper of acid on it, did not have a chemical reaction, so you will put a negative sign. Oh, look at this. The hardness is now more than 265. Awesome.
It's growing.
It is. New scale. Yes, Elizabeth?
Do I save my teacher question?
Yes, please. Okay, the next one, pretty simple. Is it magnetic? In your bag, there's a teeny tiny little magnet. If you hold the magnet up to the mineral, you will see there is no attraction. It is not magnetic, so you can write a negative sign in the chart. Okay, fluorescence. When it's dark, when you turn on the fluorescent, the UV box, does it glow? Our sample does not glow. It's negative.
So no or negative?
Negative. Are there any other unusual or special characteristics that this mineral has? How does it feel? Is it greasy or soapy feeling? I'm not going to ask you to lick the rocks or the minerals, but some of them have a taste. Some of them smell. So, smell them. You don't know who's been looking on those rocks.
I'm just saying, like,
No.
is that something, you know, like,
Okay, so I want you to look at the mineral data table. And, I mean, after you look at all of these characteristics, look at the unusual things. Because sometimes these will immediately identify which mineral it is. For example, if something tastes salty, it's halite. If something is magnetic, that immediately identifies the mineral. If it reacts to acid, that's going to narrow it down to one or two things. So look at those first. So this sample is very hard. It's got six-sided crystal with a pyramid on top. Now, to identify our mineral, got a little chart for that too. Mineral identification key. So we're going to follow through our chart. Is it non-metallic or is it metallic? It's non-metallic. Is it soft or hard? Did it fracture or cleave? Fractured. Is it light colored or dark colored? Light. It is quartz.
Science.
That's quartz.
Bam, there it is. Now, look at the next page, quartz on table 1.8. Quartz is down at the very bottom. The chemical composition of quartz is SiO2, 1 silicon and 2 oxygens. It's colorless, though its color varies. Has a colorless streak. Its hardness is 7. Its specific gravity is 2.6. The crystal pattern is hexagonal. It fractures. Conchoidal is the type of fracture that it has. And then it's used in glass manufacturing, electronic equipment, radios, computers, watches, gemstones. Examples include amethyst, agate, and onyx.
Onyx is black quartz.
It's a silicate. It is not, those are variations.
So what do we put under family?
Family, is that not on there?
Silicon?
It's a silicate. Yeah.
There's another chart.
Okay, so the next thing, yes. So guys, listen, minerals are divided up into families. We can categorize minerals according to their chemical composition. Silicates are the most common type of mineral on Earth. And all of the silicates, their basic structure is SiO2.
Quartz is an oxide.
Quartz is not a silicate.
Yeah, quartz is oxide.
Pardon?
If you're saying quartz is a silicate?
No, it's an oxide.
It's an oxide.
She said silicates are the most common on Earth.
Yes.
I thought Tanya asked what family was.
No, yes. Silicates are the most common, and they have SiO. The oxides, quartz is the simple, only silicon and oxygen, so it's considered. So just consult this table for the family. Okay. So we now have sample number 1 all done. Now the room we have 2 rooms for you to work in. And I'm going to put you into groups and send you on your merry way. Stay in here and do the tests for, in here you can use your kits to do color, luster, streak, hardness, magnet, unusual characteristics or properties. Once you're done in here, then you're going to go to the other room. I think it's 222. It's around the corner in the
Oh,
corner.
yes, 222.
Okay.
That's our lab.
Okay.
And there are snacks outside the door.
And there are snacks outside the door. In that room, you will conduct, there's 2 stations each for crystal shape, cleavage and fracture, specific gravity, acid, and fluorescence. I'm going to put you in groups of 2 or 3 so that we can move through this quickly. Good. Okay, so half of you will remain in here, half of you will remain in there. When you get done, go on your own to the other room. We have a lot of stuff to do. Get as much done as you can in the next 30 minutes, and then we'll get back in here, okay? So I want every other person on this side to be a group and go in the other room. So Elvira, Pam, and Brianna, go.
Quick question, just to clarify, 1, 2, 3, 4, 5, 6.
Yes, that's a really good thing. Yes, look at this, guys. To clarify, if you have the lid away from you, number 1 is in the upper left, 2, 3, 4, 5, 6, next row, 7, 8, 9, 10, 11, and 12 is the yellow one. Okay? Okay, y'all can take off. Yeah, leave your, straighten up a little bit. Yes, Tony?
So are all of the samples over there?
No, you're taking your samples with you. And so each group needs to have one box,
Each group needs to have one box.
okay?
Elvira.
I'm not leaving, I'm not
Elvira. How do you say?
Okay,
Elvira?
okay, Brianna, you're going with them.
They'll call me Bill.
Okay, Tanya, and Ashley. Y'all go.